Okay, so imagine one random day your $300 crypto investment all of a sudden turned into $3 million. It won't, but, imagine. Among the long list of things you definitely get are a bunch of sleek, mean, high-performing supercars. But, something you probably wouldn't buy? A manual transmission, because nobody does anymore. But back in the day, before that fateful evening in September when we all learned what compression really means, stick shifts were everywhere. And they're held together by a miracle of engineering that involves friction plates, spinning death wheels, and your left leg doing calculus. Trust me, it's insane. So buckle up, grab your seat belts, and focus up because we're talking clutches and gearboxes. The manual kind, not those cowardly automatics that shift for you like some kind of robotic nanny. Oh, I'm sorry. Did I offend your CVT? Good. Now I know I have your attention. Okay, every smooth brain out there knows that your engine spins fast, like really fast. We're talking thousands of RPMs, but your wheels, they need to spin slowly sometimes. Like when you're creeping through a parking lot looking for a spot, or when you're trying to parallel park while your dad yells at you from the passenger seat. Basically, if you connected the engine directly to the wheels, you'd have two options: stall immediately or launch into orbit like a bottle rocket. Neither is ideal, unless that's what you're looking for. So essentially, in order to make your car go vroom at the right time, you need something called a transmission. But what is it? Well, think of it this way. A transmission is a magical box that changes the speed ratio between your engine and your wheels. But for that to work, we need a clutch, whose whole job is to connect and disconnect that box from the engine without everything exploding. Make sense? Cool. Let's get science-y up in this garage. Let's start with the clutch. The clutch is basically a sophisticated on-off switch for your engine's power. But instead of flipping it, you stomp on it with your left foot while simultaneously doing 17 other things. But how does it work? Well, it all starts with the flywheel. This chunky metal disc bolts directly to your engine's crankshaft. It spins whenever your engine is running. Then there's the clutch disc, sandwiched between the flywheel and the pressure plate. This thing has friction material on both sides. Think of it like a hamburger patty, except it's made of Kevlar and disappointment. And if you burn it, it costs $400 to replace. Speaking of pressure plates, a pressure plate is the angry bodyguard of the clutch system. It uses springs, big springs, actually, to clamp the clutch disc against the flywheel with hundreds of pounds of force. We're talking 1,200 to 2,800 pounds of clamping force, depending on the car. Now we have to look at Newton's third law, which states, for every action, there's an equal and opposite reaction. In this case, the pressure plate squeezes, the friction material grips, and torque gets transferred from the engine to the transmission. But for all this to function, we need something called the release bearing, aka the throwout bearing. Rejected Pokemon name aside, this little guy pushes on the pressure plate spring fingers to release the clamping force when you press the clutch pedal. Now that you know all the parts, let's see how they work together. Honestly, the mechanism isn't hard. Clutch pedal up, the pressure plate squeezes the disc against the flywheel. Power flows. You're moving. Clutch pedal down. Release bearing pushes pressure plate. Springs decompress. The disc floats free. The engine and transmission are essentially divorced. It's elegant. It's simple. It's also why your left leg feels like it ran a marathon after sitting in traffic for 2 hours. Engineering aside, the clutch works because of friction. Specifically, static friction when engaged and kinetic friction when slipping. Yes, it's about to get a bit more science-y. See, the formula for frictional force is F equals mu times N, where F is the friction force, mu is the coefficient of friction depending on materials, and N is the normal force, which is how hard the pressure plate is squeezing. Normally, clutch discs use materials with high coefficients of friction. So, for example, organic compounds, Kevlar, or ceramics for race cars. And that's because the higher the mu, the more torque you can transfer before slipping. But here's the kicker. You actually want some slip sometimes. See, when you're starting from a stop, you gently release the clutch pedal to let the disc gradually sync speeds with the flywheel. That's called slipping the clutch. It's how you don't stall like a chump at a stoplight while everyone behind you honks. Basically, too much slipping and you burn the clutch. And trust me, it's terrible. It smells like burning hair mixed with regret. Don't ask me how I know. Okay, now that the clutch has connected your engine to the transmission, what's actually inside that greasy metal case? The answer is gears. So many gears, different sizes, all waiting to mesh together like a mechanical orgy. Here's how it works. Your transmission has two main shafts. The input shaft is connected to the clutch disc. This basically spins at engine speed whenever the clutch is engaged. The output shaft is connected to your drive shaft and wheels. This is what actually makes the car move. Between them, there are gears. Lots of them, different sizes. And here's where the magic happens. To understand gears, we gotta look at some math again, as something called gear ratio. Although it sounds complicated, a gear ratio is just the number of teeth on the driven gear divided by the number of teeth on the driving gear. For example, if a driving gear input has 20 teeth and the driven gear output has 40 teeth, the gear ratio is 40 divided by 20, which equals 2-to-1. But what does that actually mean? Well, it simply means the input shaft has to spin twice for the output shaft to spin once. You've effectively traded speed for torque. So, in a car, the first gear might be 3-to-1 or even 4-to-1. This essentially means lots of torque multiplication in, sadly, slow speed. This is what you use to get moving from a stop or climb a hill that's steeper than my credit card debt. The second gear might be 2.5-to-1, which basically means less torque but more speed. The third gear might be 1.8-to-1, and this keeps going up through fourth, fifth, and maybe sixth gear if you fancy. All you have to remember is each gear gets you closer to a 1-to-1 ratio, where the engine and wheels are spinning at nearly the same speed. So, by that law, the sixth gear in some cars is basically overdrive and less than 1-to-1, like 0.7-to-1. Here, the output shaft spins faster than the input. This is the gear you use for highway cruising, where you want low RPMs and good fuel economy. Now, this whole process probably has you wondering, how do you actually change gears? Great question, imaginary student who definitely isn't David from the comment section. See, inside the transmission, all the gears on the input shaft are always spinning when the clutch is engaged, but they're not connected to the output shaft. They're just freewheeling on it like a bead on a string. To select a gear, you use synchronizers, which are also called synchros, because engineers hate having enough syllables. Thanks to these synchros, when you step on the clutch pedal and disconnect the engine, as you move the shift lever, it also moves a shift fork. This shift fork slides a synchro sleeve toward the gear you want. And just like that, you picked a gear. Now, to pull everything together, the synchro has a cone-shaped friction surface that rubs against the gear, matching speeds through, you guessed it, friction. Once speeds match, the synchro sleeve locks onto the gear with dog teeth. Now that gear is physically connected to the output shaft. As soon as you release the clutch, power flows through that gear to the wheels. Basically, the synchro is why you don't hear a horrible grinding noise every time you shift. Well, you shouldn't hear it. If you do, you're either shifting too fast or your synchros are toast. Or you learn to drive stick in a Wendy's parking lot at 2 a.m., like some of us. But that's all cool when going forward, but what happens when we want to go backwards? Well, reversing is the oddball. It doesn't use a synchro in most transmissions, it uses an idler gear, which is basically a third gear that sits between the input and the output to reverse the direction of rotation. That's why reverse is so loud and clunky. It's no synchro, it's just raw, unprotected, metal-on-metal gear meshing. It's the transmission equivalent of a one-night stand. Now that you understand how it all works, let's walk through a full launch from a stoplight. So, with your engine running and clutch pedal down, the pressure plate is released. The clutch disc starts floating and the engine is spinning. Although at this point, the transmission input shaft is not spinning and you're in first gear because the synchro has already locked it. When you release the clutch, slowly the pressure plate starts clamping. The clutch disc begins to grip the flywheel. you get some slippage and speed starts sinking. By the time the clutch disc is fully clamped, engine torque flows through first gear, let's say a 3.5 to 1 ratio, and the output shaft spins. The drive shaft spins, and bada boom, bada bang, the wheels spin, and your car moves. As you go on, you press the clutch, disconnect the engine, and move the shifter. The synchro slides to second gear. Speeds match, dog teeth lock. And as you release the clutch, you're now in a 2.5 to 1 ratio. Less torque, more speed. From there, you repeat it for every gear until you're in sixth, cruising at 75 miles per hour with the engine humming at a chill 2,000 RPM, listening to a podcast about true crimes or ferrets or whatever you're into. Look, although the process is true automobile poetry, I will admit it's a tad bit clunky. In fact, modern automatics and dual clutch transmissions shift faster than you ever could. They're more efficient, and they don't require a third pedal. They don't make you look like an idiot when you stall on a hill in front of a school bus full of children who will remember your failure forever. But the thing is, manuals give you control. You decide when to shift. You feel the connection between the engine and the road. It's pure, it's mechanical, it's everything a car should be before computers took over and made us all lazy. So, if you ever get the chance to drive a stick shift, do it. Learn the clutch, feel the gears. Stall a few times, grind second gear like it owes you money. Embrace the chaos, because one day, all of this will be gone. Replaced by electric motors with one gear and no soul. But until then, that's how a manual transmission and clutch work. Two systems, one goal: turn explosive dinosaur juice into forward motion without turning your engine into a firework display. If you learned something today, hit that like button. If you didn't learn something, hit it anyway, because the algorithm doesn't care about your feelings, Steven. While you're at it, why not subscribe for more unnecessarily detailed explanations of car stuff? Leave a comment telling me I pronounced synchro wrong, or that I forgot to mention double clutching. I didn't forget. I left it out to make you mad. And remember, the clutch pedal's on the left, not to brake. I know someone who learned that the hard way on a certain September evening we don't talk about anymore. I'm out. Keep the revs high and the clutch smooth.